Okay, hello everyone. Today we're gonna have Rushil doing some topic which he has not told us yet. Rushil, as you might know, is an IMO gold medalist. Hopefully, you know that. He's also written this extremely good book on Olympiad combinatorics called Exploration in Olympiad Combinatorics. It used to always be out of stock on Amazon, but regression to the mean has forced it to now be available on Amazon, so you can buy it if you want. Anyways, back to Rushil.
Yeah. So after a lot of discussion and seeing that int poly won the vote, we will not be doing int poly. Instead, we will be doing defining reals. So the whole structure of this thing will be just talking about a lot of things that we use kind of casually, like the fact that they're irrational numbers and things like that. So we're going to start off with some things that probably some of you might know. For example, when we start off with the natural numbers, every uh, can anyone define how you can? Okay, I mean there are a lot of ways of doing it formally, but a very sort of broad idea could be that you start by defining a zero, and then you define what is sort of incrementing operation. So what C++ people would write as plus plus. So you define the plus plus operation on zero, and you go to one.
So why?
And then you define it.
Okay, this is a question in chat, and I also have the same question. Why
Mhm.
is zero counted in the naturals?
That's a good point. This is
You can just start with
only,
one.
only because I need some things, like for example, I will define a set of rules where I'll say something like a plus zero is defined as a. It'll just help me in the induction things. Like I don't know.
Oh,
You
cool.
could start at one if you are really that desperate. Um, but anyway, so you start at one, you define things plus plus, then you define addition. So you define a
How
plus
do you
b plus
ensure
plus.
that no a plus plus is equal to like some number before a?
Yes, so that's one of the things that you have to like define. So you have to say that k plus plus cannot be zero. So there'll be basically a set of axioms which you need to follow. And the
What
set
are
of
the
axioms
axioms?
varies based on who defines them. Like there's a set of piano axioms, there's also different sets of axioms, but that's not really the point. Basically, we can imagine getting to rational numbers by, we start with 0 to n. We also define the negative numbers so that a plus minus a becomes 0. Plus plus notation just means adding one. Like that's just a joke. Yeah, Terry
Python
Towns
people
book was
write it as plus equals one.
sorry.
I think Python people write it as plus equals one.
Yes. I don't
Plus,
understand why plus equal one exists. Like Python should just also accept plus plus, but
wait,
they,
Python does not accept plus plus?
no, I don't know why.
Yeah, I told Python is a bad language.
Okay. Anyway, so basically you can get to this point where I think Rohan also spoke about this in his previous class, where you have what is known as a field of rational numbers. Um, and essentially here you can do a lot of things. There's a lot of rules. For example, a times b plus c is ab plus ac, and there's a bunch of different things. There's like a plus b plus c is a plus b plus c, and this in general, all of these rules apply to fields in general, and as we'll see, reals are also a field because you can multiply, you can divide. Complex numbers are also a field. We have finite fields as well. But essentially what we're going to try and do over the next some time is distinguish between, so this is like a history class now, rationals, reals, and complex.
Are we going
So
to define exponentiation वगैरह?
no, we're not going to bother with the actual analysis details. Like, you can, we can talk about how you would do those things, but for now, let's think about what is common. So, rationals, reals, and complex are all fields. Now, this is already pretty interesting because, for example, integers are not a field because you cannot divide. Similarly, like positive integers is not a field because A, it's integers, and B, because you can't subtract easily. Positive reals is not a field because you can't subtract. But these three things are all fields because you can always do A into B plus C is AB plus AC. You can do A into B into C is AB into C. You can do A into B is B into A. You can do A plus B is B plus A. All of those things hold.
Can't divide by 0, right?
Yeah, but that's again true in all of them, and that's a rule of the field. So you can divide by anything except 0. That's the rule. Um, so like yeah, that exception is supposed to be handled. You're right. Um, so does anyone have any idea on what distinguishes reals from rationals?
I
Rationals.
can start. So,
Irrational.
so one thing about the reals is that if you take any sequence which possibly converges to some value, then that value is also real. The
Yes.
same thing
So,
isn't true with rationals. Like
Good.
if I take the definite approximations of root 2, they converge to root 2, but that isn't rational. So that's
Yeah.
the main.
Yeah. So what you're talking about is basically this whole thing called Cauchy sequences, where basically you have sequences that sort of converge towards a point, and like it's not so basically reals are in that sense complete. So the word we're going to do to distinguish these two is define this thing called completeness. Um, and
But
completeness is basically this property that if you like,
are we
do things in, sorry?
are we just trying to distinguish them, or are we trying to do something stronger than just distinguishment?
For
I
now,
mean, I
we're
can
distinguishing them. We will talk about more in a
because I
while.
can just distinguish this by saying absolute value of R greater than absolute value of Q.
Yes, but that kind of depends on, what exactly the reals are. So uh, just wait a little. We're just talking about intuition right now. We're not like, trying to set up like, who can give more distinguish, who knows that pi is a rational or a real and stuff like that. Um, So basically, the idea is like what has been said is that if you take a sequence like 3, 3.1, 3.14, 3.141, and like where the sequence is going, it's going towards the decimal digits of pi. And you have defined, let's say, some notion of convergence, which, by the way, we have no idea what it is yet. But let's say we have defined some notion of this sequence is converging and it's converging to some value. Now the question um, is it converging to some value? So in the rational numbers, the answer is no. So if you give me this sequence and you tell me how you're constructing it, and you ask me, is this sequence converging? I'll say no. Compared to the real numbers, where if you give me the sequence, I will say yes, it converges to pi. Um, but that doesn't really distinguish anything. Like, I mean, yes, you're saying that this sequence converges in one place but doesn't converge in another place. But yeah, I mean, so what? So, and also, I think the whole reason I don't like this whole idea very much is it's kind of like, when you talk about the sequence, it's as if you already know what's going to happen. You know that the answer is going to be pi, which doesn't really make sense if pi isn't defined yet. So this is one intuitive way of thinking about it, but I don't think this happened last time too. One,
Like in this, like the with the numbers you wrote, I can just tell that it's like 3.141414, and it still is
yeah,
converging in reals. So
exactly.
A way to
So
overcome this issue is like you treat 1.1 and then 1.11, and then the gaps will become powers of 10. And then that can be proven to be transcendental.
yeah, so I mean, I agree with you that you can define a sequence like that and that won't be rational. So, um, there is definitely some truth to what is going on, but it doesn't really give us the intuition we want on like where are these
Intuitively,
numbers coming from?
intuitively, numbers are just numbers on a line. Real numbers are just numbers on a line. So an intuitive definition would be anything you can do geometrically. But that's less than reals. I know that
That's
much.
also some sort of intuition, but imagine you were somehow able to squish the real line into a rational line, where like, I mean,
That
how are you going to distinguish between these two lines? Like, if you say that, oh, between two rationals there's a rational, between two reals there's a real, two rationals that are not equal, like, I mean, like everything still works. So it's a bit weird. So I'm going to do a little bit of magic definition.
yes,
Listen,
I got
listen
something.
for a bit.
With the
Is
real
why.
rational,
Wait, you
Okay,
could
sorry.
Someone speaking?
You could create a set of pairs of integers and then define an equivalence class and define that set modulo the equivalence relation to be the rationals. Like
Yeah.
A,
So
comma B and
that's fine. So rationals are well defined, we can assume. But we're talking about how we're defining reals.
Okay. Yeah. With a rational line, like you said, I can make constructions which do not fit on it. What I mean is that if I take a rational line and I take uh, any point on it, I can just make an orthogonal line and I can just make root 2 times that thing and I can circle it
Yeah.
and I'll see, oh,
Basically,
that
you're
circle does
saying
not
your
intersect that
argument
line.
is that root 2 is not a rational,
Exactly.
but root
I
2
can
is
construct root
real.
2. Yeah. I'm not saying it's real. I'm just saying it's not rational.
So essentially, what you're saying is, I think one thing that we can say, for example, is in the rationals, there doesn't exist x such that x square equal to. In reals, there exists x such that x square equal to. This is something that we could get at.
wait, I'm not so sure if there's any circular reasoning, but you can define the reals as like the set of all numbers which can be formed as taking a subset of the rationals and taking its supremum or infimum.
Yes,
Like-
so that's kind of similar to what we're going to do.
That
It's
I
not
think
exactly
that is
that.
the
but-
upper bound property, lowest upper bound property, which is I think equivalent to Cauchy sequences
Yes.
of something. So you'll get
Yes.
back to some circular loop.
Yeah.
So
So just to define,
can you
we're going to
speak
use
to me?
this fancy word. Dedekind cuts is basically this thing where I think of each real number as a set of rationals. So so I define a set. So far I don't know what any real number is. All I know is what the rational numbers are, nothing else. And I say that I'm going to define a set S, which is a subset of the rational numbers, which has the following properties. So property 1, and we'll see why these properties are interesting. But property 1 is that if you have a set S and it has an element, so first of all, S is non-empty. So S is not empty. I'll just say this to be clear. And I'll say that all elements of S, so if S belongs to S, then S is less equal B. So there exists some B such that this is true. So basically all numbers in your set are bounded above by some B. And the third thing is a slightly weird thing. So I will explain why these things are happening. But basically for all S and S, there exists T and S, which is bigger than S. And wait, there's one more property, sorry. For all S and S, if T is less than S, then T belongs to S. So this is some very weird thing I've done. Basically, now I'll explain what I've done. Imagine cutting the real line at some point and taking all rationals before it. That's essentially what I've done above. But at no point have I mentioned like taking any real number. So it's kind of like some cheating way of doing this. So
Which S is this? If T is more than what S?
sorry?
In the third line, can
For
you
all S and S, for
can you please
any
use
S
different
and S, if
symbols?
there is an element T less than, if there's a value rational T less than S, then T is also an S. So basically, if like 4 belongs to the set, then all rational numbers less than 4 belong to the set. And there's a number which is more than 4, which is also in your set. But all numbers in your set are bounded above by something. So yeah, the rule is basically if a number exists, then every rational before it exists. But there is no strict maximum. So there is no like final value. So any value you take, there'll be a value bigger than that in your set. But there is something.
is that how you're defining supremum of the set?
Yes. So the supremum of the set will basically be just
Wait, can
so
you repeat
but the
once?
point is
Yes.
this set represents a real number. So when you want supremum of a set, you'll take the union of all these sets, and you'll take the largest value in that. Like
Can you
the
just
equivalent.
explain it once more?
Yes. Okay. I'm going to spend a lot of time talking about this. Don't worry. This takes a lot of time to understand. So think about it like this. Let's say I want to construct the number pi. Okay, so pi exists not on the right of 4, but it exists here. Now, basically, I'm going to associate with pi all the rational numbers less than pi. So, for example, 21 by 7 exists. No, that's just 3. Uh, so, whatever. You can think of all the rational numbers that are less than pi. And this set of all rational numbers less than pi will represent the number pi. So, essentially, each real number is now a set.
But how can you say that pi is a real number? I mean,
We don't
what
know
if
what
it's a
pi is. So this is
oh
why,
pi?
yeah. So we don't
So pi
know
is
that
like
pi
three.
is anything.
As of right now, pi is a variable, just a variable.
No, we don't know anything actually. We have basically what I did right now is I started with pi and I defined the set. But what we're doing in practice is we're starting with the set and then we're saying, oh, this set represents pi. So just start with a set which satisfies some properties. So it satisfies the properties that it's upper bounded, and it satisfies the properties that if something is in the set, then everything less than it is in the set, and it satisfies the property that there's no maximum element. The maximum element thing is slightly unnecessary. It only is used in some other things when you need to, let's say, multiply things. Some things can go wrong if you don't do it. But the two main properties that you need to think of is that if there's an element in your set, everything less than it is there, and there's some upper bound. So basically, you take any such set, choose any such set, and this will correspond to exactly one real number. And then one of those real numbers happens to be pi. So
Wait, but like, if we have a real number that's less than pi, but then our numbers representing pi are less than that, something like little slightly less than that, then can't we have two representations for us for different
yes,
reals?
so good point. So let's imagine we have two real numbers. Now, the key idea we will use is basically there is going to be a rational number in between these. So,
Sir, what if we want to say that 0.999 is not equal to 1? Like you're assuming 0.999 equals to 1 type things.
no, I'm not defining anything like that.
I mean, what you're assuming that in real numbers works like that, right? I mean, you just said that real numbers and between any two real numbers is a rational number.
No, but 0.99 and 1 are the same number.
Yeah, I know that, but like this kind of assuming that. I
Okay,
mean,
so listen again. Like we don't have any idea what the real numbers are. All we have idea about is sets of rational numbers. You agree that every set I can construct in this way is a distinct set because if two sets were the same, then they're the same set. So basically, there are lots of different sets you can make, and each of those sets I will map to some real number. I have not yet decided how exactly I want to map those numbers or whether this works or how this works. This is what I want to do. Basically, every real number is now a set. And now let's imagine you want to add two real numbers. It's basically saying that you have two. So imagine you don't know what A and B are. You don't know that A is
Would it
3.1,
be
B is
taking the
5.6.
two sets and then considering the pairwise sum of all pairs of elements from the two sets and then
Yes,
considering that set?
exactly. So A is not a real number, guys. A is a set of rational numbers.
A
And
is a
B is
set.
a set
Then you
of,
do like set wise A plus B and then you do stuff.
yes. So
Like
you
it
do a
should
set of
ideally
A plus
satisfy
B.
the same properties.
What?
Like if you do the sum addition, it should ideally satisfy the same properties, I think.
So listen. So basically now we're going to prove that this whole thing makes a field. So when you do something like SA plus SB, this will be equal to SB plus SA. So it satisfies all the properties that a field was supposed to satisfy. Um, so in
Wait,
particular,
like if we just prove this isn't just the satisfying comment, what's it called? Communicate something.
commutativity.
Yeah, isn't just that satisfying just that and feel satisfy everything like that this associativity, distributivity, etc.
No, commutativity does not imply these properties are made in a way that no one property implies another one. They're all properties that need to be checked.
Yeah, so like why are we only proving SA equals SB equals
Yeah,
SB?
this is one of the things. I
One
agree.
of them.
We'll have to prove everything, but that's also not something we will end up doing because that would just take a lot of time.
Wait,
I mean,
how do you prove that none of these quantities imply like any of the others, even in combination?
sorry, what? I didn't understand.
How do you prove that, say, for example, commutativity and some other stuff doesn't imply associativity, for example?
Find a
I
counterexample, right?
Yeah, you can define some sort of operation which satisfies some subset of them, but it doesn't satisfy some other subset of
Oh,
them.
okay, cool.
Yeah. Okay.
Wait,
So
multiplication be defined in the same
yeah,
way.
multiplication is the annoying thing. That's the annoying thing
Really?
because
Yeah,
because
but you'll have to go to the equivalence classes in rationals.
What?
you have to do something
Can't
because
we
of
just,
positives and negatives messing you up. Because
can't we
basically,
just do if
Ah,
zero
oh, you know,
is
that is
smaller
not
than
as
zero?
hard. But that you use something like distributive property, if I'm not wrong.
sorry. No, the point I was making is if -100 is in your set of numbers less than 5, then -100 into -100 can't be in your set of 5 into 5.
Yeah, but what you can just do is you can consider it case wise. Like
Yeah.
if they
Yeah,
are
exactly.
positive,
That's what
then
you'll have to do. You'll have to split it for greater than 0 and less
Why
than
do we
0.
need all the reals anyway? We'll just define the positive reals and define negatives to
Yeah,
get a negative of it.
yeah, you can do that as well. But then you need to be careful about a few other things, like, for example, we'll see later, like completeness can become a little bit sketchy. And also subtraction, you still do need to define pretty well. So, like, it'll be messy, but it'll work. Um, so, but does everyone get the idea of what this set addition means? This SA is a set of rational numbers. It's like Q1, Q2, and like till infinity something. And SB is again a set of Q2, no, maybe R1.
how do you define smaller than any way?
Sorry?
How do you define smaller than any way?
So this is a funny thing. A is smaller than B if and only if SB
I'm
is
thinking no, rational
Find
numbers. I'm
the
thinking
same
rational
spot
numbers.
there.
How to define smaller than?
smaller. What do you mean smaller?
How
Yeah,
do
how do
you
you define that?
define the binary operation of being
Oh,
greater than over the
I
rationals?
mean, take their
Yeah.
difference. Is it positive?
How to define positive?
Okay,
Okay,
good
so that
question.
is an
We'll
action.
define. We will
Can you
define
define it?
positiveness
Can
also.
you define
I
it
mean,
as
for
like
rationals, it's fine because you can just what the natural numbers are.
Isn't it
Right.
just greater than 0?
Yeah,
That is
but
cyclic.
but the
Never
point
before
is
did I think
natural
that I
numbers
would
are well
hear
defined.
the question, what is positive, and actually be stumped.
So no, the point is what I'm saying is if you have rational numbers p by q, you say p by
Hmm.
q is greater than r by s if and only if ps minus rq belongs to the natural numbers union 0.
Okay. So you take
Uh,
rational numbers as sets of two numbers.
yeah.
No, but then you can just
Then what about
replace
like
q with minus q
replace?
and
What about like with like
Okay, I
positive
mean,
factor?
sorry, we can just say qs. Does this work?
Yeah.
Sure.
yeah, that's good.
Okay. Um, but but that's not the interesting thing. The interesting thing is how you would define greater than equal on these real numbers. And that is by just subset. SA is the subset of SB implies that A is less equal B. Um, so okay, this can be done. Multiplication, as I said, is slightly annoying because you need to split it into the positive part and the negative part, work with them separately, handle your cases, and it will work out. And basically what you'll get is now you have defined some sort of field. We have no idea that this field is actually the real numbers. Um, and there's no reason to believe that, let's say, root 2 belongs to this field or whatever.
I mean, what
Um,
is root 2 at this point?
yeah, so what is root 2? It basically is a number such that if you take there exists basically a set such that when you multiply that set with itself, you get the set representing 2.
Okay.
So the question is there a set like
Wait,
this?
just a minute. Does this definition allow you to take supremums directly? Like,
Yes, exactly. So that's the powerful reason why Dedekind
Then you
has
can
so.
define root 2 by this
Yes.
being a set of rationals.
Oh,
Yes.
so you like just take all of the such sets which have like x squared less than 2, and then you just like look for like whatever the lowest or lowest
Upper
like thing
bound.
it's bounded by.
Yes. So we're going to talk about this thing called the supremum of a set, which is basically the so we'll take two assumptions. Set is non-empty, and set is bounded above. So there is some upper bound. And the cool property that real numbers end up having, and this is equivalent to completeness. So this is what I would define, in fact, as completeness. Um, right now, at least. When you work with complex numbers, for example, you don't want to define completeness like this, even though complex numbers are complete, because there's no notion of bounded above on complex numbers. And we'll talk a little more about that.
You can just define an order on complex numbers, right?
So we will talk about that very soon. But before that, I just want to talk about this. So the real numbers have this magic property that there exists a least upper bound. And what this means is that, like, essentially there is a upper bound on all the elements in your set, which is at most any other bound. So the formal way of putting that is, there exists T such that, so if your set was S, for all S belonging to S is at most T, and for all T dash such that for all S belonging to S is at most T dash. So if T dash is another upper bound, implies T dash is at least T. So T is the least upper bound. So this is some cool property that turns out to be satisfied by the real numbers. And in particular, it's also satisfied by these sets of rationals. Because what you can do is whatever your set is now, if you think about it correctly, a set of sets, a set of rationals. And then what you can do is take the union of all of these sets. And that will represent some some set, and that set will correspond to some real number, and that will correspond to the supremum. Because, okay, basically what I'm saying is that if you have sets S1, and notice that the number of sets here could even be uncountable. So these are some details that you would have to think about in terms of set theory, whether it's legal to do these things.
You have to
But
do Zorn's lemma, right?
no, the number of
What
elements in all
lemma?
of these sets is
Zorn's lemma.
countable.
Zorn's lemma is something which is equivalent to the axiom of
What did you
choice.
just say?
No, but we don't need that here. I'll tell you why.
What did you just say? What was your question? I couldn't hear you.
Zorn's lemma. He's asking basically whether does this depend on the axiom of choice.
Does what depend?
The fact that we can take the union of uncountably many sets here.
Why would it? Can't we just say that if we have we can just define the set which contains element if and only if it is in one of those two sets?
Yes, that can become slightly messy. Sometimes here it doesn't, because each set itself has only countably many elements. So these are things you would want to work with if you're like doing set theory. We assume that set theory things are well understood when we define reals. Um, so like that's not for right now. But basically what is happening is if you have a bunch of sets where each of these sets really is representing a real number, and you want to define the supremum, you define the supremum of this, so I'll call this T. You define the supremum of T as the union of Si, where it's not exactly good notation to do this because there could be uncountably many things, but just like believe me on this.
How would he? Yeah, that's the point. How would he do it in? Oh,
So yeah, what you do in practice
uncountable.
is for every rational number, check if it is there in any of these things. And that's something that's legal to do using set theory. Like,
But wouldn't it require axiom of choice? Like you're making a choice
no,
function.
you're not making any choice. You're just checking if there's a rational in this.
How do you
how
define
would
making a
you
You
choice?
don't need to pick at any
Yes,
point.
yes. So like you can create like infinite lists and then each that is
Wait,
so
I don't get what the issue is though. Like, what?
The issue is that uncountably many things work a bit weirdly. Unions don't always work well with uncountably many things. For example,
Okay.
the basic union definition is only defined for taking countable unions, where there are only countably many things.
Sure.
So you need to mix up the definitions a
then
little
you
bit
can
for
then for this you could also define infinity to be the set of all rationals. So like if it's unbounded, then it becomes the set of all
yeah,
rationals.
but I mean I've assumed that it's bounded above all of these
Oh,
sets.
yeah.
can you just like how would you intuitively think about the supreme once again?
Yes, so that's a very good question. So maybe that's something I should have done before. So let's take the set where x square is less than 2 and x belongs to rational numbers. What's the supremum of the set?
Um,
Root 2.
It should be root 2, no?
Yeah, basically the point is if um like basically first what we can show is that the whatever the supremum of this set is, it can't be rational. Like this, if the supremum was some rational number q, which was, let's say, such that, so then you would check what is q square. Q square could either be more than 2, less than 2, or equal to 2 by trichotomy, which is like every
I what?
trichotomy is the formal thing. If for any two elements a and b either a is greater than b, a is equal to b, or a is less than b.
What? That's something.
Yeah.
I
Yeah,
mean, I guess when you're defining stuff, you have to be rigorous about this.
Yeah.
I'm so happy that I see other people getting annoyed by this and not me just because I've already
No,
done
I'm
this.
having fun.
I'm also having
Okay.
Yeah,
Well,
I'm
you have
getting
q
another.
square can be greater than 2, q square can be less than 2, or q square can be equal to 2. And actually, let's not even assume q is rational. Q is just some number. Um, Actually, we have only defined rational numbers. We have defined real numbers as sets. So think of this as, okay, the set squared, is it greater than the set 2? Because we know what, so like, if you get what I mean, SQ into SQ, is it a superset of S2? Is it a subset, or is it equal?
Wait,
um,
how are you multiplying the sets?
yeah, I have not defined that very formally,
You
but
can do
basically
it like similarly to the way you do set addition. Like,
No,
no,
but
that's
then
the thing.
negative.
It's not that similar.
But then you can
But
just take like the positive values if they're there, and then
yes,
that will help.
yes, exactly. So we will split into the positive parts and the negative parts and do the multiplication separately, essentially. And yeah, it's a little bit annoying. I've never actually seen someone describe it formally to me because everyone says, "Oh yes, it can be done." We never talk about it.
what can be done?
What?
anything can be done.
Yeah, anything
That's
can
just
be done.
wrong. Not anything can be done. There
Wait,
are lots of things.
what is S2?
anything can be done if you just assume it to be an axiom.
Okay,
That's
guys,
a
listen.
maximum false.
That is
Okay, let's focus.
So whatever this supremum is, we're going to show that the supremum square is equal to 2. And
Okay.
the proof of that is if the supremum
If
squared
the
was,
supremum square is less than 2, then you just take some element larger than it, so that supremum square is like,
yeah, but you need to have a rational number which has
okay,
to be quite less than 2 but is
Then
more
you
than
can use the density of rationals.
you can use what now?
Density of rationals.
Basically, we're not using
Any
in density of rationals, we're using the binomial theorem, guys. So if q
Yay!
square is equal to 2 minus epsilon for some, okay, epsilon scares people sometimes, I'll use t. So now I'm going to use epsilon anyway. So I'm going to check what is q plus epsilon squared. So it's equal to 2 minus t plus epsilon squared plus 2q epsilon by binomial theorem. This is q squared. And I'll define um okay, yeah, you will need density of rationals now that I think about it. But like the basic
Can't you
idea,
indirectly do
at
it?
least for the intuition here, is that you can choose epsilon small enough so that this number is still less than 2. And you can make this a rational number. So it will be a rational number which is more than q, but it's in your set. So that contradicts the fact that this is an
But
upper
you will
bound.
be in terms of epsilon. Wait, your
Sorry?
side. That seemed a
To
little.
make it rational, how do you
So
make it
here,
rational?
this is the thing. This is like thinking about light. You know, when they tell you that light is dual, like it's a wave and it's like particle.
Just
Now you have to
decide,
think of a
physicists.
now you have to think
Very
of a
good.
real number simultaneously as a number which you can square and use binomial theorem on. But you can also think of it as a set where you can take like, like check whether a set is a subset of another
Wait,
set.
okay,
Or,
in the set definition, how do you prove a plus b whole square is equal to a square plus 2ab plus b square?
because it's a field. And every field a
Factorize
whole squared is as
distributive
simple as
property the
the
same way you do it normally.
Yeah, but like distributive property might be a bit hard to work
It's
with.
assumed in a field, right?
Yeah, if you can prove all the field properties for the set definitions, then we would be fine.
A
You have
square
to
plus
prove it
a
in a
plus b
field.
square equal
Wait,
to
why do we need like density of the rationals or whatever? We can just directly do it, no?
How?
Okay, so we want to say, so we're saying ki we can make epsilon square plus 2q epsilon take arbitrarily small values.
Yeah.
Okay, so let's
But we
say,
need q plus epsilon to be a rational.
if you keep epsilon to be rational.
But q may not be rational.
No, q, what?
Wait,
Oh,
why?
right.
Oh,
Okay.
right.
And also, then you need that rationals go, like, even if q was assumed to be rational, you would need that there are arbitrarily small rational numbers.
1 by
which is
10 to
Yeah,
the
yeah,
end.
equivalent
that
to
you
density of
that I
You
was
can just do
assuming.
like 1 by 10 to the end, right? That works.
Yeah,
Like,
yeah, you can, but that's essentially assuming that like 10 to the n goes to infinity, which is how you prove that rational numbers go to zero. So you're
Isn't that
assuming,
like if q is rational, then we can like write down an explicit function that is like larger than q but less than square root 2. I
yeah.
do not know the motivation of that function. I have it somewhere.
I
I'll
see.
just look it up.
No, but what you can
you
do,
have
which
this
is
function.
kind of silly here, is
Yeah.
like you know that q has to be less than 2. So you can like kind of drop this q and you can say epsilon is less than 1. I'll assume that epsilon is less than 1. So you can just make this like 3 epsilon, like 5 epsilon, and then I can just choose epsilon less than t over 5. Something like that.
Can we not use like limit extends to 2 minus or something like that?
Limit. Who taught you that
What
word?
is a
I have
limit
never
now?
heard of it in my life.
I wonder what the heck this newfangled gizmo called a limit is.
Yeah, so limit is not yet defined at all. So far, what we have come to a conclusion. Okay, so this was, by the way, all just intuition about what we are doing with squares. When we define the thing formally, we don't do any such risky stuff of knowing whether or not rationals are dense or not. We just say sub T is the union of these sets. Um, that union is a set, but that set represents a real number. So the sub T is a real number. Um, and the question now is, why does it satisfy these two properties? The first property is satisfied because obviously any element you take here, Sk, will be a subset of the union. That's again some set theory stuff. And if you assume that there is anything which is a superset of all of them, then it must contain everything in the union, because if not, you can create a contradiction. Like assume that there is some element in Si which is not there in T, then like you will run into problems, because then there will be some specific set which you will not be a superset of.
Is the set corresponding to two all numbers below 2 or all numbers below or less than or equal to 2?
So that's what I was very careful about here. When I said for each number there's a number bigger than it, I made sure it's less than 2. There's no less equal scenario. Basically, like this ensures that whenever you have a number, there's a number bigger than it. So it's always going to be an open set. Like it's always going to be something like in minus infinity comma 2. Never this. Because there has to be a number bigger than 2 if 2 is there in the set, based on the way I've defined these sets. That's why this property is kind of important. You can ignore it. Like you can say,
Wait, like in this set, if there has to be something that's bigger than 2, what there should be something that's bigger than that number, which is bigger than 2 also, right?
yeah. So are you saying that hence there are arbitrarily large numbers?
No, no, like I am saying that if you include that something that's bigger than 2, you have to put the close bracket there, right? Because you can't go because
No, if
it's
there's something bigger than 2, then this is actually not this. This is not that. It'll actually be something like 2.1 like this.
like
Possible.
suppose a thing that's bigger than 2 is like suppose 2 point something. So
Yeah.
in 2 point something there will be a close bracket. Why are you writing?
No, no, the point is no matter what number you pick, there will be a number bigger than it. So for example, imagine this set. All numbers less than 1. Then any number in this set will have a number bigger than it. But then I can say this is this comma 1, right? All numbers less
Yes.
than 1 has this property. So basically
Uh,
any set I will end up with will have this open bracket. That's the only.
right. Got it.
Okay. So anyway, so the reason why, so there are a lot of definitions of the real numbers. One of them was what Adit was suggesting at the start, something like taking sequences and checking whether they converge. So that's a very much equivalent definition. But the thing is, for real numbers, people like this word called supremum because they like to use it a lot. And then the question is, which definition of real numbers makes it easiest to prove this? And the answer is this, because the proof is one line. Take this. So that's why people like this definition a lot. But also it's extremely
Wait, that's a proof
honestly,
or a definition?
hmm?
I thought that was a definition.
Sub T is defined like this, yes, but the point is it satisfies this property. So
But why is it the same thing as what we intuitively call real numbers?
okay, good question. So the point is, what are real numbers?
Yes, so when I say real numbers, I mean the real, that is what I think of when someone, at least when I hear real numbers, I think numbers on a line.
Yes. So 1 second. So basically the word we have added right now is complete. So reals have this property called being a field. They're also complete. One question I want to say, one point I want to raise is complex numbers are also complete. Though you need to change the definition of complete slightly because now there's no, and this is actually
You
going to
don't
be,
have order.
this
Wait,
is
so
going
what's the new definition of complete?
reals are also ordered, whereas complex is not ordered. So let's talk a little bit about what is order.
Could you order
Um,
lexicographically, like on the pairwise components?
So
Exactly, you could do that.
let's talk about it. You can define an ordering, but you will never want to, is the point. Um, so basically what everyone wants is there to be a well-defined notion of a positive set. When I was doing Ollie at some random point, at some point I had this idea, oh, what is the square root of I? Of course, it's possible to evaluate this because square root of any complex number, like any complex number can be some other number squared.
And for some reason, normally it's two numbers, which just really weirds me out.
Yeah, so the point is that like I is e into I to the pi over 2.
Okay, what does this mean?
We'll talk about okay, we could talk about that, but we'll do that in a complex analysis, a real analysis.
Yeah,
Here,
theta is cos theta plus I sin theta, something like that.
yes,
Negative.
that
No, cos theta. There's no cos theta. Sorry.
basically, the intuition I try to give to this is that I think of e to the anything as just this thing.
But like, how do we get e like all of a sudden just a random number from the number line
Is this Taylor?
Okay,
satisfying
but
this
why does
real
this
condition?
converge now?
Again, a good question.
Because
Now that's where real analysis comes back. That's where we will that's what
Also,
we will do once we've defined convergence in real numbers.
this
one more thing. Aryan said about you can use this, you can prove this using Taylor series. Even for that, you need to prove like convergence and all the stuff for like
One
infinite
second.
series.
Using what
You
series
can't
now?
use Taylor series to prove this because this is how I define it.
No, no, not this. The e to the power I theta equals sine theta plus I cos theta plus I sine theta. That thing.
That is
Euler
just
form.
Oh yeah,
sine theta is also defined using
but
the
that time you need Raymond's rearrangement stuff. So you need some
yeah, you will need a lot of
Wait,
things.
okay,
Let's
at
not
this
get
point,
into
what
it.
is
Yeah.
defined and what is not defined?
So the
Basically,
way
nothing
I
is
think
defined.
about it is none of this is defined yet. We're just taking a brief jump to think about what complex numbers are. Once assuming that we know everything about real numbers. And while we're defining that, we we think of e to the x as this thing, which makes sense for real numbers to us, because we have proven that it converges and it is like absolutely
I have a
convergent and
question.
everything. Go
Yeah,
ahead.
I was saying that like we are defining to the power like e square e cube. How are we defining like e to the power x where x belongs to real? Like e
Yes.
into e, it's
Again, good
like
question. Whereas that's what everyone is thinking right now. Like everyone thinks that when you want to define 2 to the pi, like how do you do this? Or maybe e to the pi is a cleaner
E to
thing.
the 2 ln pi, no? I mean, e to
So
the
they
pi
define
ln
it
2.
like you take a sequence approaching pi and then you take e to that and then you can define
That's one way of thinking about it. The way I think about it is just do this, right? 1 plus pi square by 2 factorial plus pi cube by 3 factorial.
like if you define x
Multiplication
and
is
then
fake. When people say a square is a into a, this is fake. A square is like e square is not e into e. E square is 1 plus e square by 2 factorial plus e cube by 3 factorial.
It is
Wait,
also
what?
equal to e to e.
Sorry, 1 plus
Wait,
That
wait,
is
wait,
also
wait, wait, hold on. So we define it for integers as the multiplication thing.
And then you check, what you check is that it turns out to satisfy this property that e
Okay.
to the x into e to the y happens to be equal to e to the x plus y.
And then you extend.
Yes.
wait,
Okay.
how would you prove that x and e to y e to x plus y with this definition?
You need a lot of absolute convergent stuff. Like basically each of these are absolutely convergent. When you're multiplying to absolutely convergent, you need a lot of things to work out.
Wait,
But
so
but
like,
like you are doing but like you are doing for e, but for a general real number, how are you doing it? Like there is no like obvious Taylor.
when you say 2 to the x, I just think of it as e to the
e to
x
the
ln 2.
ln.
And ln 2 is a number which is defined by ln x is equal to 1. This is another
No,
Taylor series.
no,
Why
no.
can't you just
Define
ln of x is the inverse of e
in
to the
this,
x?
if you put x equals 2, you will get e into e.
wait, you can define ln of x as some integral, like integrate the area under the curve. Like
Why are you
negative.
Yeah, but
cos
then you
plus
need to have defined integrals already. I would much rather have ln defined
No, no,
before.
I'm asking that if you put you get e to the x equals 1 plus x square. If you put x equals 2, you will get e into e there.
Sorry, x equal?
X equals 2.
Yeah, if you put x equal 2, you will get e square. Yes.
You will get
And
e into
at e square will be equal to e into e. Yes. Like basically the property you will get is that if you ever think of these two series and you multiply them, it will be equal to 1 plus xy plus x square y square by 2 factorial plus blah blah blah. This is something
Should
that
that
can
not
be
be
proven.
x plus y squared?
Wait, why won't there be just extra terms all over the
Oh,
place?
sorry. I messed up. You're right. This is x plus y. This is x plus y whole square. So,
At this point, this is what probably comes up in some generating functions book, I guess.
Wait,
Yes.
could we
so
prove
let's forget about all this. The reason we had come to all of this is because I said e into I to the pi over 2, and this was equal to cos pi over 2
cos
plus
pi
I
by
sine pi over 2, because e to the x, cos x, and sine x are all defined by Taylor series. Anyone who told you anything else is like lying to you. These series are how cos x and sine x is defined.
Can't you
You
define them
don't have
using other
anything
methods?
known beforehand. What?
Can't you define them with other methods? For
you take a
example, the
polynomial and
definition.
you
No, of course
differentiate
you
it
can
out of
define it with other methods. I'm just
Okay,
saying
no, no.
like
Like
this.
first we got that cos x and sin x are triangle. That's wrong. Then we got it's in circles. That's also wrong.
Yes, that's entirely
fine?
no, but the point is that is a very limited way of thinking about these functions.
But
Okay,
Like
what
like
is pi at
I
this
believe
point?
from the pure geometric way with no real analysis, you can get to the sums with a geometric proof. Like I saw it in the Mathomaniac video. But now the main thing is like, how do you prove cos square x plus sine square x equals to 1 just to Taylor series?
You can. Anything you can think of with Taylor series can be proved with enough effort.
Wait,
Yeah.
so does it also make sense to take cos of an imaginary number in
Yeah.
general? Like, is it done
Yeah.
So,
usually?
Yeah.
You're against bashing, but you are pro doing all the
So
algebraic.
I am not pro multiplying these things out. I am pro believing that someone can multiply them out
I
and it will
have
be
no motivation for expanding out random polynomials or whatever it was on Aryan's AOPS thing.
So that's
okay.
each good.
So let's get back. What I was saying is I is this thing. And the point is then we have the square root of I, and the problem is that can be e to the I into pi by 4, which is half plus I by root 2. But it can also be the conjugate of this. So half minus I by root 2. No, maybe negative of the whole thing, actually. Sorry, not the conjugate. And if you square each of these things, you will get to I, as you would expect. But the point I want to raise is, which of these is the square root?
The first one, the positive one, I guess.
Both of
Maybe
them are square
square.
Positive
roots.
one. Very nice,
Maybe
very nice words you have used.
maybe square root is just a social
Not a
construct which only
like
exists in the
You
real.
don't
okay,
even know what
maybe like
positive is.
the
Please,
Sir,
basically
how
what I'm
do you
saying
positive
is,
distinguish
one, but
between I and minus I?
you need to
That is
have a
why,
notion of positiveness.
sir,
Um,
first,
That you
how
don't
do you
have in
distinguish
the
between
complex
first one,
numbers.
not the positive one. Sorry.
yeah, no. So I understand what you're trying
Positive
to say.
real part, because like one of
Basically,
them is x,
one thing
one
you
of them
could
is
try,
minus x.
is everything on this side of the plane, except possibly like this line is the positive, everything else is the negative. But what goes wrong is when we look at square roots, we assume one very basic thing, and this is how usually people prove 1 equal minus 1, because they do this.
Yeah, the root x into
That's
root
just
y.
wrong.
Oh god.
This is supposed to be true. If everything is done correctly, this is true. It's just that in complex numbers, square root is not well defined anymore.
So
So
square root is a social construct.
You
yes.
can only do this if both are greater than zero. I guess I'm not using positive anymore, but I guess that's the
Yeah.
thing.
So the point I want to make is that the social construct is that if you take two positive numbers, they should multiply to a positive number, which is
okay,
not
so
true.
why can't you
Because
just
if you
define positive to be a number such that its argument is 2 to the power of n for n integer plus pi k for k integer?
because there is the rule that out of x and minus x exactly one has to be positive.
Then you can do that.
Okay, so
Also, why can't we do this? I actually don't know. Like, uh, for a complex number, you can define the order by the tuple r comma theta. Theta is between 0 to 2 pi. So lexicographic
yeah,
on
yeah,
r comma theta,
yeah.
and then define square root as the one with the higher order, because you said square
Higher
root like
order, higher angle.
no, not angle. Okay, yeah, r will be same for both of them. So
Yeah,
higher angle, and then
yeah.
whatever you have to do, you like adjust using that thing. Is
So
that
if we
not?
assume
Basically,
higher
basically what
angle,
you're
then
saying when you say higher angle, because the two angle options will be one will be like in this area and one will be in this area. You're saying pick the one in the bottom half of the plane.
Yeah,
Right. You're saying why can't the positive numbers be defined as the bottom half of the plane?
sure.
And
Yeah.
the point is that the product
Mirror
of two
symmetry.
positive numbers should be positive is the notion we accept. And if you assume that, then the product of this number with this number would lie somewhere here. Or
No,
actually,
maybe in this field we don't accept that notion. We say product of two positives is negative, and everything
yes,
else should still
product of
stay in place.
if you assume that notion, then yes, you can define an order, but then lot of things that you need get messed up because now inequalities don't work out the same way you expect them to. Like if you
Sir,
assume
why can't you do something like you have most numbers as positive or negative, just a few numbers are neither positive nor negative. Basically, what I would do is I would take an arbitrary irrational angle. Irrational matlab modulo pi, like the sense ki pi k plus that value is irrational. I would take any arbitrary irrational and I could just double it up and then
okay,
half it
I'm going
down.
to
I
prove
would
to you
consider
that
those positive.
if you assume that product of two positives is positive, then there can't be an order on the complex numbers.
No,
Because think of
but
the
you have to also be including that a number is positive or it's negative
yeah,
order. I
yeah,
don't do
yeah.
that. I say ki,
That and
I can
that
say I and minus I are both not positive
How
in my
is what
case
how is what you wrote true that if x minus y is
because
positive
I
and a
square equals to because you have
oh,
to say
does
I square
not
equals to y.
imply like this. This does imply, of course, but it does
Yeah.
not imply if you forget that product of two positives is positive. Like that's why product of two positives being such an integral property to the whole notion of ordering. Like you
And
can't
you
do
can't do
something.
that because it's an extension of real. So you would want that property to remain.
Yeah, yeah,
Makes sense.
and yeah. The point is okay. Think of I and minus I. Which of these is positive? Let's say I is positive. Then I square is positive, so -1 is positive. Bad. If minus I is positive, then minus I squared is positive, but minus I squared is also -1. Bad. Problem.
So why can't you just say
So
that certain number
Okay,
and then
okay.
all
Technically,
numbers
I've
with
cheated a bit.
basically,
Technically,
complex numbers are scuffed.
yes. Also, one thing I've said,
that's-
-1 could be positive, but if -1 was positive, then -1 squared is positive, so 1 is also positive. So -1 and 1 are both positive. Contradiction.
Oh wow.
why can't we just have that
Why
-1 and
not?
1 are
Okay,
both
I will
no.
not
not
lie
positive?
on the like I will
You
not
need
lie on the
exactly
graph.
one of x and -x to be positive. That's
But like
So
I will not lie in that
that
graph
is
at all. Like,
that is
I will
simply
lie
wrong. I can just
somewhere
take x equal to
abstract,
0.
some
So I can
what?
simply take x equal to 0. That's wrong.
No. So okay, the exact rule is out of either exactly one of x and -x is positive unless x is 0.
Then I can just so I'm saying why can't I just have for countably not countably I can have measure the like
No. That's
negligible
not the
number of
point.
exceptions.
You want these rules to work. The rules that work in real numbers, you want them to work in complex numbers, and you just can't make that happen. That's the problem.
I can make them work most of the time though.
Yeah, you can make them work most of the time, but like that's not
Exactly.
enough.
Why is that not enough? Why can't I just have most of the time works?
Because then you have no control over whether it's going to work. Like it could work, it could not work. Like that's like saying, like, I mean, then you might as well like think of a probabilistic field or something.
Yeah, I mean you can
But
do that,
anyway,
right?
listen, coming back to this, the real numbers have this very nice thing that you can define an order, so you can define a set of positive numbers. And now we have three words: complete ordered field. And it turns out that if you assume that a set has these three properties, there's exactly one set, and that has to be the real numbers.
Okay, okay.
How would
There's
you
only one set that satisfies all three.
wait? You could prove that with some sort of category theoretical ideas, like you define
You don't.
You
category and then
can
you
what?
define
What?
Category theory is like like proving trivial stuff like for no reason.
Can
Not
someone
like
can someone get
no.
me an Atharv dictionary for specifically when Atharv is speaking?
Yes, please. I also want it.
Okay, guys, ignoring all that, basically the point will be think of any set that is a complete ordered field. Then we will show that there is an equivalence in this set with the real numbers so that you can associate, basically, if there's any set, you can kind of create a bijection from that set to the real numbers so that everything works out the way. So like, for example, if you took two elements in this set and you saw their maps and you added these numbers, then the answer is what is the same real number you get here. And then if you multiply them, that also works out. So it's what you would call an isomorphism between these two things. And the proof is not particularly fun. It's basically because it's a field, there will be something that you can define as 0 and 1. You can use that to define the naturals. You can use that to define the rationals. Once you've defined the rationals, because it's complete, you can do this something like very much like a Dedekind cut. It's kind of like it's basically like a phantom point in Geo. Like you don't know that it's going to work, but because you know that it has to work, you just assume it in backwards and like it just works. And then the order part comes in preventing you from doing more things essentially.
So
like it blocks
reals are the only completely ordered fields.
exactly.
Containing the rationals.
No, like complete
That
ordered field.
do they not like surely you can just say
I can
that there's a
trivial field.
complete ordered field not containing the
Yeah,
rationals.
so there is such a set, but that has an isomorphism with the reals. So I think
Okay.
of
No,
it as
sir.
real numbers.
Why can't I just take a trivial field? Set containing only 0. That's
Um,
complete, that's ordered, that's a
First
field.
You
of all,
can't
fields have
can
at
you
least two
divide?
elements.
Does division make sense? No, everything's
Fields
zero,
have at
so
least two elements. There
division
has to
doesn't
be a
make
0
sense.
and a 1 in a field.
No, but like satisfies the one properties.
Yeah,
Yeah,
what if
but field
0
has to have
equals
at least two
1?
elements. Field
Yeah,
has to have
0
at
equals
least.
to 1.
You should add a field axiom that 0 is not 1.
That's true. But that was not the
That,
field axiom. That was the natural.
yeah, that is the axiom you require only for fields which have more than one element. And I mean, yeah, that's only required
So
for when
there's
you
a
have one
nice
element.
way to
That's a
define rationals assuming the reals. Basically, you take this, you define this concept of an inductive set. So an inductive set is something that contains 0, and if x is in the set, then x plus 1 is also in the set. and the set of naturals is the set of the intersection of all all inductive sets.
Kind of like that P set problem.
Which we
That
said
kind of makes
Like
sense.
the one with like x by x plus 1 and 1 by x plus 1.
yes, sort of like that.
So now that we understand all of this, how do we put this to use in our brains? Because now every time we think of real numbers, we can't be thinking of sets. We can't be thinking about like this. The main thing, the magic part of real numbers is this word, sup. This like anything that you can do in the real numbers, but you can't do in the rational numbers, is all because of the sup. So the sup is actually integral to pretty much everything that we'll prove right now. So let's prove a bunch of things. Let's first prove a few silly things. Can you prove to me that the natural numbers is not bounded? This is called the Archimedean principle.
Assume it's bounded. Say there's a bound by x.
Just
Then
prove there are
Take the
infinite frames.
supremum.
and take the
Just prove that there are infinite frames. Done.
So
and take the
basically,
supremum and then take the
assume it's bounded by some b. So like
But
let's say the
like,
supremum is s, but
okay.
then there so by this there's this very cool property of the supremum which says that if you choose any epsilon, there's always an element in the set which is between s minus epsilon and
Isn't that like the definition of supremum? Like
yeah, I mean that's almost equivalent to the definition. Like I mean this is just true because if not, then this would have been a better upper bound. Like basically if
Okay,
there's
wait.
no element here, then s minus epsilon is an upper bound.
Wait,
Right.
what is epsilon?
Epsilon is
Any
any
number you choose.
small positive
Any
number.
number you choose. Doesn't have to be small. Choose whatever you like.
Small can be big in some contexts.
Any positive number, to be fair. Can't be negative.
Any positive number. So you're telling
Yeah.
that suppose B is the maximum in naturals, then what is your argument again?
Sorry?
What
I'm
was
saying
it?
that if the supremum of my set is S, then there will always be some X belonging to S that satisfies this. Because if not, if there's no such element, then S minus epsilon is an upper bound.
Ah, okay. Makes sense.
So yeah. So yeah, so the point is if the natural numbers were bounded, then it was bounded above by some X. So there's an element in this. So I'll just choose epsilon equal half. And then whatever that X is, X plus 1 should satisfy X plus 1 is more than S plus half is more than S. So but X plus 1 is a natural number by how natural numbers are defined, because X is a natural number. And so contradiction, S cannot have been an upper bound. Okay, but that's how you do silly stuff for no reason. There's a lot cooler things you could do. So let's do some cool stuff. We're going to prove that if you have any sequence that's bounded above, okay, actually maybe that's not that much fun, because that's also kind of silly. Okay, I'm going to give you guys a very funny question. So you have a function. Now we're going to define functions from reals to reals, right? So basically every real number gets mapped to another real number. And in
What is the
particular,
formal definition of a function?
like for every real number, it's like a function from a set to a set. Like
no,
every
it can be function can be thought of like a subset of R cross time R cross R.
yeah, that's a good idea.
Yeah, the Cartesian
A set
product
of
of
R cross R such that each thing on the left thing is chosen exactly once.
No,
And
Okay.
Formal
more than
definition of
one.
mapping, what can you say?
what?
Formal definition for mapping.
Yeah, so a subset of R cross R such that the left element, okay, so I could say, so F is a subset of R cross R if F also satisfies the properties that for all x belonging to R, there exists x comma y belonging to F, and for all so if x comma y belongs to F and x
And
comma z
like
belongs
X
to
comma
F,
Z, then Y equals Z.
then y equals a. So there's a unique x at every point. So whatever. So there's a function, and we don't really need it to be defined from reals to reals. We will only need it on a subset. So basically from 2 comma like 0 comma 1, let's say. And it's a continuous function. So we're using a very big word here. We will talk about what a continuous function is. We want to show that it's upper bounded.
1 by x.
What do you mean 1 by x? Like it's 0 to 1, like
Okay.
Closed set or open set?
closed set.
It's defined from R to 0, 1.
Yes.
From 0, 1 to R. We'll talk but so temporarily let's imagine you guys know what a continuous function is. We'll talk about the formal thing as well. But continuous function is,
The limit from both sides are zero.
yeah. Yeah, that's I guess what we'll go with for now. Limit from
Wait,
both
it's
sides.
not the right definition?
It is, but we don't know what a
What
limit
a
is yet.
limit is.
Epsilon delta definition works.
What is epsilon delta?
Definition is key.
Epsilon
If
delta
for
is
any
these numbers.
for
I
you
can
can't
go
define
as
limit.
close to the function as I want.
yes, basically that.
Basically.
Or whenever x is in the neighborhood of some a, then f of x is in the neighborhood of some
Okay,
n.
okay, forget all that.
Ulta.
Prove
Okay, I
this,
think of
guys.
an idea. So
Prove that
basically
it's
say it's unbounded. So
Okay.
you split the interval in half and then it's unbounded on that also on one of the two sub-intervals.
Yeah.
And then you split it in half again and again. And then somewhere you get in a very, very tiny interval that it's unbounded. But somehow we could try showing that leads to a continuity contradiction.
Wait, motivation where?
No, like
No, I mean
it's a very simple thing done in a theorem called Bolzano-Weierstrass. Basically, you have an
so
infinite.
we're going to talk about Bolzano.
I need the dictionary, guys.
Basically the idea, Athar, what you said doesn't work directly. Then you would need the interval thing that, if you take a subset of decreasing intervals and it converges to a point, like you would have to start talking about that. So I'm going to actually talk about this slightly differently. Basically, assume it's unbounded. So then there exists some number which is bigger than, let's say, 10. So if I make the line of 10, there's some number bigger than 10. Let's make the number 11. And there's some number bigger than 11, some number bigger than 12, etc. So basically, I'm going to say f of xi is greater than I. I'm going to define a sequence like this. Like this can be done if the function is unbounded.
And then it belongs to sets, and then the union, the intersection of the sets, and then it converges.
Now it is actually Bolzano-Weierstrass. So okay, basically there's a very cool idea which says that if you have a sequence, any sequence, where all the numbers are bounded. So let's say the sequence, all the numbers are from 0 to 1 here in particular. X
Oh,
naught, X
okay, okay. The limit you can take a okay, fine.
you have a convergent subsequence. So there is a subsequence in this which is converging. And again, lot of terms that we have not defined very well. But the point is then f of those things, because of the way continuity is defined, will also converge somewhere, but it's supposed to converge to infinity, which doesn't make sense. Contradiction. So this is the sort of cool stuff that you can do. We'll have to talk a bit about a lot of these things. But actually, before we even talk about that, another thing, actually something we can prove directly right now without you assuming anything, is the intermediate value theorem. So
okay, I mentioned it in the chat. Let's go.
So let's imagine there's a function again from reals to reals, such that at 0 its evaluation is -1 and at 2 its evaluation is 1, so that it must cross over 0. It's continuous, of course.
We could do something
Maybe like take the values where this function evaluates to something negative and take the supremum.
Yes, exactly what we
And like do something if it's like not 0. I don't know.
Perfect. Yeah, no, that's exactly the idea. Basically, take all x such that f of x is less than 0. So this is set now. And because of the way continuity happens, like if you're at -1 here, if you're within like some closeness to -1, the value has to be close to -1. So basically, this set is basically non-empty, is my claim. I mean, first of all,
And
minus one
then,
itself
you
is
split into
but
intervals and you keep on splitting, and then the intervals converge to something.
yes. So your interval thing also works, and in
Wait,
fact, the interval thing is a very common idea.
isomorphic
So
to this.
it's
Wait,
like
would
what I
that
like to think of as binary searching.
wait, would the interval thing be isomorphic to this? Like in a sense, like because
Mm,
you keep on splitting and one thing is negative, so like the
What is
negative
isomorphic?
approaching.
it's kind of like an equivalent approach, let's just say.
Yeah.
I mean, isomorphic approach is not well defined anyway.
Yeah. Isomorphic approaches we call isomorphic.
Yeah. Okay.
Like they're
Anyway,
basically equivalent.
it'll not exactly. I mean, of course, all proofs have to be equivalent in some way of thinking about life, but not directly. Um, okay, guys, listen. Take all x such that fx is less than 0. Take the supremum of this set. So take the largest number so that fx is less than 0. And we'll show that this supremum, whatever this value is, f of s is 0. Because if not, if f of s was less than 0, like if f of s was here, then if you go very, very close to s, then f of s, like let's assume f of s was minus 0.1, then there is a choice of epsilon such that, so this is where it would have been useful if we knew the exact definition of continuous. But basically, you can choose epsilon such that f of s plus epsilon is at most is at least at most I don't know, like it's
At
basically
most, it
very
should
close
be
to
at
minus
most.
0.1.
Here you want to do something like negative epsilon, like minus epsilon, since like you want it to like you drop down a bit and then it's still greater than.
No, you want the supremum to be even bigger, right? If it's negative, you can
Oh,
go
it's
even
negative
further.
0. Oh, I thought you dealing with 0.1, not
Yeah,
that.
yeah. So,
My bad.
so yeah, the point is basically you can increase your supremum a little and it'll still be no, wait. Yeah, you can have a number bigger than the supremum, which is a contradiction, in your set.
Okay.
Okay,
And
and if it's larger, then you just because it's
then you can
continuous,
make a
you take
smaller supremum. You can have f of s minus epsilon
yeah.
will also be greater than 0. And everything in s minus epsilon to s is anyway bigger than 0, so we don't need to care about that. So s minus epsilon is also supremum. So this is why supremum is such a powerful thing. Like, just one word and like it's just like doing things that, by the way, like intermediate value theorem just doesn't hold for rational numbers. Like you can still define continuity for rational numbers and everything, but you like if you have f of x equal x square over rational numbers, this will never take 1 over 3, even
Wait,
though
you
it
can define continuity for rationals?
yeah,
I mean, you
exact same
just need
definition.
stuff to get closer to stuff as other stuff gets closer to other stuff.
Yeah, the point is basically rational numbers also have the property that they can become very small. That's the only property we need.
I think their density over reals.
Dense over reals is not relevant because reals as a whole aren't relevant.
Also, I would have wondered, like, what is small? Is it like negative minus a very big number or very close to 0?
Very close to 0 always. Small numbers
Absolute
never close to
value
0.
is as low as possible or something.
Yeah. Yeah. Okay. For what it's worth, let's define limits and stuff, because I think that's something that okay, does someone want to do it for me? So let's first define this limit of a sequence. So a1, a2, and so on is set to converge. So lim an is equal to L if, does anyone want to speak up?
For all like x, like for all x like
For all
greater than
epsilon.
0,
For all epsilon, there exists
there exists some y such that like for all n greater than or equal to y, we have mod of an minus L is less than x or epsilon, I guess.
Yeah, exactly.
Like, won't you have to define? Wait, you can also define it like you take the supremum and infimum limit, and then
yeah, lim sup and limit.
Yeah.
Yeah, and they're equal. Yeah.
That's actually a more generalizable definition.
Yes, that's true. That works, especially because the whole, this doesn't make sense when you work with complex numbers. But you can actually do it because you can, I think.
Wait, why
also, like,
doesn't this make sense when you're doing complex numbers?
because less than doesn't make sense.
but absolute
Oh,
values.
absolute value.
Yeah, so that's
Also,
why
like
it is fine. That's what I just
that
realized.
that means
You
like
can take the distance from origin and it will be fine.
that means just complex numbers have continuity,
Complex numbers have continuity, yes.
but you can't make complex numbers as small as possible, can you?
Of course you can.
You can.
Be better to think of complex
Like
numbers.
Reals are a subset of the complex numbers, so just
no,
take some real
So
sequence.
okay, your notion is correct. You can't define small, but you can define their modulus to be small. So yeah, you will have to always say. So you'll have to define what is known as a metric, which
Yeah,
basically reduces any set, whether it's the complex numbers or matrices or whatever. You can define a metric on that set to show how far it is from zero, basically, which satisfies properties like the triangle inequality, like mod of a minus, like mod of a plus mod of b is always at least mod a plus b, things like that. Like you define a metric which satisfies these properties, and then you define continuity and everything using that metric.
but then after we go into the notion of metric space, so now we can define continuity of a function. Like
Yeah.
function is continuous from one metric to another if I think every convergent sequence in one converges in the
Yes. So I mean, yeah.
Okay, now stuff is starting to go over my head a bit.
No. Basically, what is happening is if you have a function from a function from, let's say, we'll just imagine reals to reals in our head, but any set to any set, and you take a sequence that converges towards a point, like converges towards this point, then f of those things should also converge to some point.
Okay.
They should converge to the same point. So that's like basically what we're saying.
Wait, isn't there one definition of continuity that the map of every open space is an open space? Something
Map
like
of every
Now
what is a
that
what
takes
now?
a lot of effort to prove. Like I don't think
I've still not been able to prove
What
it.
is an open space? As far as I'm concerned, an open space is like
Even
outside my
it's
house.
actually a lot like an open interval.
Yeah, exactly. It's like it's an open interval, but like generalized to, let's say,
Basically, you can
circle.
find, like, it's like everything which, okay, we'll not get into this, guys.
Where is this topic
That's
heading to?
math that we can do. And if you're defining, by the way, when it's not a sequence, when you're defining functions limits, then you say limit extending to x naught f of x is L if, and does this make sense to people? Basically, no matter what distance you need from your sequence, eventually you will always be at most that distance. So basically, for example, if your sequence converges to 2, then eventually you will always be between 2 minus 0.1 to 2 plus 0.1. Always. Like it's not possible at every 10 trillionth term, suddenly you become far away from 2.
So
Then it
as
will
the
not be
physicist said, your error eventually becomes zero.
Yes, exactly. But error eventually becomes like
As
always.
small as you want.
Yeah, it can't be that, just once in a while you become large error. That is not fine. Like you need the error to just go to 0. And this is almost the same thing for all epsilon greater than 0, but now it changes slightly. There exists delta such that whenever 0 is less than, is greater than, no, less than. I really can't do this thing, signs of things. Okay, so that if 0 is this, then f of x minus f of x naught is less than epsilon. So basically, if you make x very close to x naught, then f of x is very close to f of x naught. So basically,
It
no
should
matter
be
how
like mod
close
of
you
f
need
of
to
x
be.
minus L,
Isn't
right?
it like the other way
Not
around?
f
Like
of x naught.
you want to make
Sorry.
F-
You're right. Yeah. This, what I wrote would have been continuity. So basically, if L is also equal to f of x naught. Of course, there is also the big question: when does this limit exist? Exactly when there exists an L satisfying this. Exactly when there exists an L
Wait,
satisfying.
L is the limit, right?
Wait, how do you show that there exists a unique L? Like, what if there are two?
Good question.
Then you
That's
can
not hard to prove.
like
Oh,
look
yes.
at the gap between them and it
The
gets
gap and it
arbitrarily close
half
to
of them.
both. So
Like if
like
we take the two L1 and L2 and consider L1 minus L2 by 2,
Exactly.
Yeah, exactly.
Yeah, so you pick L1 minus L2 by 3 to be safe. And basically, eventually you will have to be within L1 minus L2 by 3 of both of them. But
Which
then,
is not possible.
yeah. So that's why there's at most one limit. Yeah, and okay, there's a lot of interesting things to look up. I think, for example, if you're actually interested in learning this, there's like there's some Oxford notes on this, which are also publicly available. So I'll probably send a link to those on this stuff. And I think it's pretty well explained there. So that's quite nice.
Is napkin good?
Napkin is great. It doesn't explain this stuff too much. It just kind of assumes these things as formulas.
Napkin goes in like the fields, groups, and stuff.
So
Yeah,
What about
if I
just
want,
using a textbook?
if I want absolute pure rigor, then napkin is not like the
Yeah,
best
no,
choice.
napkin was never meant for pure rigor. Napkin is only to gain intuition, but it's
Okay.
really good for intuition. So I definitely recommend napkin. It's just not like, yeah, it wasn't meant to be a pure
Rigorous.
rigorous
Okay, cool.
Yeah.
Wait, napkin is not rigorous?
Yeah, Rudin is not for this stuff, I assume. No, napkin is pretty rigorous in the sense that everything they say is like fine, but like it also like
You don't start like from complete scratch.
most textbooks also don't do that, to be
Why
fair.
not? Like
Apostle does start from complete
Yeah,
scratch.
Yeah, some of them do, some of them don't.
Like Tom Apostle defined like all the reals and addition, and we never use it.
Which textbook?
Even
Tom
in Rudin
Apostle
chap 1, there's
book.
this 9-step proof of Q to R, which is overkill.
Can you just send it the book ka naam on the chat?
No,
Yeah.
it's just Rudin, it's already there.
No, not Rudin, the Apost something.
Apostle, yeah, Tom Apostle.
Tom Apostle
Just
is
Apostle's
the
Calculus
author.
Volume 1, that's it, yeah.
Also,
Okay,
I
thanks.
heard about Tao's book on analysis. Is that good?
Yeah, that's the first place I learned it from. It wasn't like groundbreaking. It just helped me get an idea of what I want to do in this
The
thing. But
starting-
I didn't
the
actually
starting
understand what real numbers are when I read that book, for example.
I see.
Station of plus plus was I think popularized by Terry Tao's book only. Like S plus plus is increment. I always thought of it as S prime, but S plus plus was the first time I saw S plus plus was in Terry Tao's book.
Yeah. No, the Terry Tao book actually spends a bit too long working with naturals and stuff.
Yeah, I got that.
Like I think
Detailed by that. Like
takes it a bit too long to actually reach what real numbers are, by which point it's also not. I mean, they've done the whole Cauchy sequence definition.
Wait, do
So,
you have the physical copy of the Tereta book?
yes.
I
Like
have
we got it at
We got
IIM.
it for free.
I'm looking forward to that next year.
Why
Hopefully.
can't we just
Not gonna jinx
download
it.
it? You can download it. You
Yeah,
know
it's
that,
there.
right?
Okay, we should stop recording.
Yeah, we should.